Okay, so our next talk is going to be by Emily Gilbert, who's from University of Chicago and actually helps run the astronomy tab at University of Chicago. And her talk, quiet down, Mr. Roca. Her talk is going to be on Proxima b, our nearest exoplanet.
Hello, and thank you for having me here. So today I'm going to be talking about our nearest exoplanet. So this planet is orbiting our closest star, Proxima Centauri, and as we've mentioned already, astronomers are really not good at naming things. So the planet is called Proxima Centauri b. Very clear. So about a year ago, this planet was discovered. There was a flurry of media attention, so there were lots of articles that came out. I particularly like this one because it gives a lot of credit to my talk. Astronomers just discovered the most important exoplanet in history. So relevant. So here is a completely fictional artist's interpretation of what this planet may look like. So be wary of that when you see exoplanet articles in the news. Most of these are just complete visualizations. So just a little bit of information about this planet. It is close to us, and close is a relative term, so that means it's 4.37 light years away. And Proxima Centauri, the star that it orbits, is actually part of a triple star system. So it's part of the Alpha Centauri system, which is made up of the stars Alpha Centauri A and B, again with the names. And those orbit pretty close to each other at about 23 AU, so roughly the distance from our sun to Uranus. And then Proxima orbits 13,000 AU away from these two stars. So you can see right here the artist has included that binary star system Alpha Centauri A and B. Proxima orbits really close to its star. It's got an 11-day orbit, an equilibrium temperature of 234 Kelvin. And what's exciting about it is that we think it's in the habitable zone, and it's roughly the size of Earth. So it's 1.3 Earth masses, so we think it's rocky. So Jen talked a bit about radial velocity earlier, so you all should remember this, hopefully. So this was how the planet was discovered. You look at the star, and you can see the star wobbling back and forth due to the motion from the planet. So they orbit their common center of mass. You can see the center of mass right here. And as the planet moves towards you, everything gets blue shifted. As it moves away, everything gets red shifted. And so through this method, we were able to discover that our closest neighbor does in fact have a planet. So here's a little bit about the Proxima Centauri system. So Proxima Centauri is right here, or Proxima b is right here. So just inside the habitable zone, this green area here. And here's a comparison to Mercury's orbit. So you might notice it's really close. It orbits every 11 days at about 5% the distance from the sun to Earth. And it has an equilibrium temperature of 234 Kelvin, which, if you add in an atmosphere, should be nice and toasty. It should be able to hold liquid water on the surface. But how is it so cold if it's so close to the stars? It's because it's around a particular type of star called Dwarf. So here's a diagram that is very near and dear to the hearts of us astronomers. Going along with the naming things, we're not super great with our diagrams either. Bear with me. So on this axis here, you have basically brightness and size. So the higher up you are, the bigger and brighter the star. And on this axis here, you have temperature. It's kind of a little confusing. The temperature goes the opposite way from what you would expect. So these stars down here are the coolest. So dwarfs fill out this regime right here, and they're anywhere from 0.08 to 0.4 the mass of our sun. They're very small, very cool, and they live for very long times. They're super active stars, and they make up 70% of stars in our galaxy. So remember this for the future. There's a mission coming up next year called TESS, which you'll hear a bit more about. And TESS is going to find a lot of planets around dwarf stars. And so you'll sound really smart at cocktail parties. You're like, oh yeah, dwarfs. I know all about them. So as you may have noticed on the introductory slides, they asked for a nickname, and I gave my Twitter handle, Dwarf. So I study dwarfs, and hopefully you remember my name is Emily. And also, as I'm sure you've probably noticed, I'm not especially tall, so I think this Twitter handle is hilarious. So back to the science. Proxima b is of interest to us because it's so close, and obviously the follow-up question is, can you live there? Can anything live there? Is there an atmosphere? You need something to breathe, so an atmosphere is important. Unfortunately, Proxima b doesn't transit, so it doesn't go in between its host star and us. So we can't see what's surrounding the planet. So if the planet passes in front of the host star, light can shine through the atmosphere, and then we can tell what it's made of. So we can't figure it out that way if it does or does not have an atmosphere. Additionally, it orbits really, really close to its star, like I mentioned before. So that means it might be tidally locked. So think of our moon, the same side always faces the Earth. The same thing might happen here. The same side of the planet might always face the star. So one side will be nice, toasty, warm, but then the other side could be really, really cold. And so there's a possibility that the atmosphere on the other side would be dense, and then you're just left with a big pile of ice. You don't have anything to breathe. Very sad. And another thing I mentioned, if you remember, dwarfs are super active stars. So there was a study done recently about whether or not Proxima b could sustain its atmosphere through all this stellar activity. So really good for sci-fi, really not so great for life, turns out. So they modeled this system. They used an Earth-like atmosphere and magnetic field, and saw how it evolved over time. And sadly, the atmosphere did not survive, but there is still hope. If it had a stronger magnetic field to give it more protection, then perhaps it could still maintain an atmosphere. Also, if there's excessive volcanism on the planet, you could produce more atmosphere than that matter. It's definitely a system worthy of further investigation, in my opinion. Turns out, I'm not the only one who shares this opinion. It's definitely worthy of investigation, and if I had money to blow, I would do something to investigate the system further. Turns out, this guy does have money to blow. So this is Gilbert. He's a Russian billionaire tech investor guy, and he teamed up with these two other guys you may know, Stephen Hawking and Mark Zuckerberg.
Hawking's poor.
But Miller has the money. So they have made the Breakthrough Starshot Initiative. So they are planning a mission to go and investigate Proxima Centauri b locally. They're sending spaceships there, or at least they want to. So here's a little bit about their idea. So they plan to launch a mothership spacecraft. And then this spacecraft will deploy 1,000 teeny spacecraft inside of it. Then each of these spacecraft will deploy a giant solar sail, you can see here, or a light sail. And they estimate that they can make each of these 1,000 little spacecraft for less than the cost of an iPhone or so. And they're sending lots of them so that you can mitigate the risk. So there's lots of dust and debris that it could hit on the way, and also you're trying to hit a moving target. So the star system's moving, the planet's orbiting around the star, so why not send lots of them, and hopefully we'll have a better chance of getting data. So once they've deployed the sails, they have this idea to accelerate them with lasers. Bear with me. So they need a 100 gigawatt phased array of lasers, which is approximately equal to the output of 100 large nuclear power plants. So a lot of lasers. They're going to zap the spacecraft for 10 minutes and accelerate them up to about 1/5 the speed of light. And so at this rate, it'll get there in like 20 to 30 years. And so they estimate it'll take about 20 years of development, give or take, and then 20 to 30 years to get there, and 4 or 5 years to get the data back. So minimum, we're looking at 45 years for this mission to happen. So I'd like to just raise a glass to medical advancements. Hopefully we'll be there when the data comes back. And so here's a quick visualization of what's going to happen. Giant lasers zapping the spacecraft.
It's like spies like us.
We get the sound effects in a lot of
There's no sound in space. I'll have to make sound effects. here. I know this whole thing seems a little crazy, but it's actually not as far off as you may think. So this is the prototype spacecraft that they would send. This is a chipsat called a Sprite, and it's got a bit of a rocky start, but they're doing okay right now. So chipsat started off, they had their first mission and launched to the ISS, and they were mounted outside the ISS, and turns out they were mounted on the side facing away from Earth. So we don't know if that first mission actually worked. Then there was a second mission, and this was a CubeSat, so a 10 by 10 by 30 centimeter satellite, and it was actually funded through Kickstarter. You may have heard about it. So it was called KickSat. And the buy-in was you could buy one of these teeny spacecraft that would be deployed from the CubeSat. But they had some technical difficulties with their countdown clock, and so unfortunately the spacecraft were not able to be deployed before the satellite burned up in the atmosphere. But third time's the charm. It's okay. In June, there were two satellites that launched, a Latvian satellite called Venta and an Italian satellite, Max Valier. And each of those had one of these chipsats mounted on the outside. And they actually got contact back. So we have working chipsats that they could potentially use as a prototype for this future Starshot mission. So the final chipsat will have cameras and photon dusters, power supply, nav, comm system, and that sail attached. But the chipsat itself without the sail is 3.5 by 3.5 centimeters, which is roughly the radius of the bottom of your beer here. Just for some size reference, you can see the fingernails there. So very, very tiny. There are obviously still challenges. That giant laser array is non-trivial. They need to make sure they can get comms back from 4 light years away. You have to have really good pointing for that and really strong signal, which is really hard to do on a tiny spacecraft. And who knows what kind of data we're going to get when you're taking pictures at relativistic speeds. However, there are some really cool science that you could do there. So maybe they could take images, maybe they could see additional planets and moons. You could investigate the magnetic field in the atmosphere and see if, maybe it is habitable after all. And what I think is really cool is you can take pictures of the planet itself. So right now, our images of planets are just a couple pixels, just a white dot on the page. And so being able to see surface features would be really, really interesting. You can see if the planet looks like ours, it has oceans and continents. So you might question whether or not it will actually make it there, but humans have been building and exploring for thousands of years. We've built pyramids, we've built skyscrapers, we've got planes, trains, automobiles, and now spacecraft. So I think eventually we will take to the stars and make it there, and I look forward to see what we will find. Thank you.
Questions?
Yeah.
So, a couple months ago we heard about the TRAPPIST-1 and its planets. You were pessimistic about Proxima B's atmospheres. What about the TRAPPIST-1?
Okay, the question was, do the TRAPPIST planets have atmospheres? So for those of you who don't know, the TRAPPIST system was a 7-planet system that was discovered a couple months ago, similarly around an M-dwarf. Does someone have more information on this topic?
No, there's 10 posters of
There are
TRAPPIST-1
10
to be
posters.
distributed.
And fitting for this event, the TRAPPIST-1 system, it was found by a Belgian group of astronomers, so it is in fact named after the TRAPPIST-1 spheres. But it also has the similar product. It's around an M-dwarf star, and they're super active. I think Proxima is actually more calm than other M-dwarf stars, and so there's more of a chance of Proxima B having an atmosphere. But don't quote me on that.
So, when you're talking about binary and trinary systems, obviously it depends a lot on the size of the stars. How stable are the orbits of these planets? I mean, we're talking highly elliptical orbits, or, you know...
Yeah, so the question was the stability of binary and trinary systems. So we actually think a majority of stars are in binary systems. So depending on the orbit, they're relatively stable. So the one that I was mentioning is mildly elliptical to people. But it obviously depends on the orbit. Some more elliptical ones are less than others. But when you throw in the third object, it tends to make it more chaotic. Does make it more chaotic. And this system, they actually just realized that Proxima was a part of that binary star system recently, because it's so far away and moving so slowly in that orbit around those two stars.
So the majority of the orbit of the planet is in the habitable zone. I mean, it's not being pulled out by the other stars now.
Was the question about the
planetary orbit?
Oh, okay.
Because that, I mean, that's going to pull them. It's hard to
Yeah. So this one is far enough away that the orbit of the planet is way, way confined to the star itself. So
The other two are 13,000 AU away.
The other two stars are 13,000 AU away, and this one orbits at 0.05 AU. So you've got some distance there.
Yeah.
But for closer in systems, that is an issue that we think about. It does tend to make it more unstable. Any other questions? I see people pointing, but I don't see any too many. Yeah.
How long are those fires?
So the question and comment was about the excessive power of the lasers and how do you prevent someone from using it for evil. I imagine there will be a lot of security around that system. A lot of death Yeah, so there will definitely have to be some new legislation regarding laser safety and access that some legislator in the future will have to deal with.
How sustainable first?
And then how long do you have to fire the lasers? You require 10 minutes of firing the lasers in order to accelerate. They have to be really, really light spacecraft. So in order to power these really, really light spacecraft up to 1/5 the speed of light. So 10 minutes each and then 1,000 spacecraft. It's a lot of laser time.